Matlab, I'm explaining about digital filtering with examples using Matlab. First example, designing butterworth filter using this equation. Another example. In this example, designing a low-pass Butterworth filter with a cut-off frequency of 800 Hz.
In the literal A, we have to find the discrete representation of the Fourier series of a periodic sequence. For this, we have the sequence x1 of n equals to these two functions in the interval from 0 to 39. First, we create the function discrete transform of Fourier, in which we have two input values, which are the function and the period of n, and we obtain as a result a vector of rows for the coefficients of the discrete Fourier transform. For our exercise, we have the following parameters: n1 that goes from 0 to 39, x tilde 1 which is the function, and n1 that represents the numbers of samples that are, in this case, 40. Applying the discrete transform of Fourier for x tilde, we have a vector of 40 complex numbers corresponding to the discrete transform of Fourier of our main function. In the end, we have to calculate the magnitude and the angles of the Fourier discrete transformation, applying the following line of code. To visualize the result, the initial sequence, the magnitude and the phase of the transformation have been plotted discrete Fourier of the original anointing. For the literal 2, only change the value of n and the domain of time the following graphs as a result.
Hello, I'm Frank, and in this part I'm gonna explain you how it works, the algorithm in the exercise 5.4. Yep. In this part, have a Chebyshev filters, and the Chebyshev filters have this form. Okay. Now, in the Matlab, this form is represented in this part of here. We can represent the form of the filter, and to represent the real and imaginary parts of the poles in our control system, we have this part of here. Yep. And finally, we must transform this part in an only equation to finally graphicate and see the response of our filter. The response we can see with this command. Yep, we can see that it's a passband filter. This passband filter have an attenuation in these parts of less 3 decibels and less 3 decibels, and pass the signal in this region. Okay. Now, in the exercise 5.5, we have an order of Chebyshev filter. We have a cutoff frequency, and it's 2, and the less 3 decibels are our attenuation. And with this command, we can design our continuous filter, calculate the frequency response, and finally see our response of our filter. Yeah, we can see the magnitude of our filter, it's the form logarithmic form, yeah, that it is represented with a bow diagram. And that's all my explanation with two kind of filters.
When the magnitude sample is zero, the corresponding angle is not zero. It is due to a particular algorithm used by Matlab to compute the angle part. Generally, these angles should be ignored. Plot of DFT values is shown in figure. The plot is also shown has a dashed line comparison. From the plot in figure, we observe the gives, for example, but has only one non-zero sample. Getting a constant or signal DC. This is what is predicted by the DFT, which has a non-zero sample at k the same zero and has no values at other frequencies.
Hi, I'm Vladimir Pachacama. I'm going to explain about the exercises 5.7 and 5.8 of the book Advanced Control Using Matlab. In this part, we talk about numerical and quantization effects for high order filters. Well, in the exercise 5.7, illustrates that we cannot successfully run at 7th order elliptic low pass filter in single precision in the expand polynomial form. One reason being that the result filter is actually unstable. However, we can readily implement the same filter in single precision if we can use for cascade second order section. In fact, for the application, the single filter precision implement in SOS is indistinguishable from the double precision implementation, given that the average error is always less than 10 elevate to less 6. In this part, we can observe a command of Matlab. This command ellip, we can design elliptical pass low filter, high pass, band pass, etc. The main feature is that the Q slope is steeper than the Chebyshev and Butterworth filters. However, it has a marked corner the cutoff frequency. In this command, we can have N, RP, Rs, Wn, when N is the filter grade, RP band attenuation, Rs curing band, and Wn frequency in hertz. We can observe in the Matlab the filter grade is 7th. It's for that reason designed as the 7th order. The band attenuation is 0.5. The curing band is 20 and the frequency in hertz is 0.08. In the second line, we consider the step response. Here compute filter in double precision, and this part is the computer filter in single precision. This command we can convert to SOS in full precision. Well, we run the program. In this moment Matlab is running, and go. In the figure, how we can observe, the red signal is the single precision, while the orange signal is the double and single SOS. For the other place in the exercise 5.8 shows how we can use FB2 to validate the design of filter with a stop band between 0.45 and 0.5 with a minimum less 3 decibels gobble and less 30 decibels in the stop band. This command FB2 opens FB2 and computes the magnitude response of the digital filter defined with numerator and denominator. Using FB2, you can display the phase response, group delay, impulse response, step response, pole zero plot, and coefficients of the filter. Well, in this moment we can run the program. And we can observe the figure. Well, in this figure we can observe the magnitude response of the filter generated by FB2. Well, it's all for these exercises. Thanks.
I talk about the exercise 5.9. The function created in this exercise is P is D. This function will use the Fourier transform to compose the signal into different frequencies and display information. Since we have assumed that the input signal is real, that we know that the Fourier transform will be conjugate symmetrical about the Nyquist frequency. Then we can throw the upper half away. Then of create the function. Now view of the graph of this code. We have the next graph. Well, now I talk about of the exercise 5.10. In the exercise we need to exercise some care in doing the convolution because the polynomials given by Butter are reaching in decreasing powers of sit. In the listening 5.10 tests the smoothing differentiator algorithm. Now we can to observe the code of the exercise 5.10. Thank you.